Hi everyone. Today's topic is recommended system. So as you know, recommended system is one of important applications with the graph data. So as an input, so we take user item rating triples. So we ignore rating information. So we just utilize their interaction. For example, we may just utilize whether the user purchased the item or not. In that case, we just ignore the score wise the rating information. Anyway, we take the tuples for items that the user has explicitly rated. They typically represented as a user item matrix. And for the output, the same tuples for items that the user has not rated. So it can be thought of as filling in the missing entries of the user item matrix. And most algorithms infer missing ratings based on the ratings of similar users. So we'll give more examples. So in short, as an input, we take the observed information and we try to predict the user item rating tuples that the specific user has not rated. So which means we can predict the user is likely to purchase or like the item or not. So we'll give you the graph structure from user item bipartite graph is given like this. Here is the user dimension. Here is the item dimension. So one means the user takes the item or not. We may put the rating information, something like this. So you may think you can regard this information as a zero or non-zero, the input. So this adjacency could be presented using this graph notations. So user one is connected to the item 2 and item 3. So it is from this information. So in this graph, as you know, there is no interaction between users and between items. That's why we call this graph as bipartite graph. So the interaction could be only between the different type of node, between user and between item. So we call this type of graph as bipartite graph. So what other information we can have? Maybe we can have sequence graph. So we have this user behavior sequence information. So per the user, we have this behavior, maybe some visiting behavior or the purchasement behavior. We buy the user purchased the first item and second, third, and second, fourth. So he or she bought the second item 2 times, and we have these sequential information. And this could be formed as the aggregated graph information. Okay? Here we ignore the sequence data, and we can take the static graph form as like this. Here H went to here, 2 to 3, and 3 to 2, and 2 to 4. But we still have the direction information. What about leveraging social relationship between users? In the recommendation domain, the social relationship is one of the important information, because we try to predict similar users, and that helps to predict the user's future behavior, right? When you are able to predict, for example, the students who take the same class as you, your schedule, and you can, for example, Coupang and Amazon is likely to predict their behavior depending on their course. And when they take some writing class, they are likely to order the textbook, or sometimes they ask some project-related product, such as some circuit board or some supplementary materials, and depending on the social relationship, the recommendation performance could be improved, right? What about knowledge graph? So when the observation around the item user interactions are very sparse, the knowledge graph helps, or it helps to understand why the user purchased the item. It is related to the user's preference and the item's property. So we don't have the details about the items and the users, so we use the knowledge graph information as well. For example, so some users purchased the Toy Story book, or the souvenirs like toys and, I don't know, notebook, pencil. And the reason why the user bought the item is maybe it is cartoon, or they are a big fan of the Walt Disney's the cartoons, or maybe he or she likes the Woody, right? So we can understand their behavior. So let's first look at the traditional approaches with the user item bipartite graph data. So here is the rating data is given. We have multiple users and multiple items. In this case, the movies are given. So we are currently try to recommend the better movie or drama or sitcom in the Netflix content. So based on the previous the user's rating, we try to predict the score, right? When we predict this about this movie, when we predict the 0.5, which means the positive expectation, and then we can give the movie to the top of the list the user can see. So we can utilize this expectation for the better service. So this is the traditional approach. Let me start with the fundamental form. So the most popular traditional approach is to use SVD, singular vector decomposition, because the input is presented using the matrix representation, adjacency, right? So the user movie information could be decomposed into eigenvectors and eigenvalues. So in other words, so U is the left singular vector, and V is right singular vectors, and here S contains singular values. So the code-wise, so you just take the adjacency from the input. So we have here two-dimensional NumPy variable, and here let's convert to the matrix, and we directly decompose and get the singular vectors and singular values from this SVD, the function call. Right? So assume that we have this information. So to predict some score, some movie's prediction for the specific user, and we just realize now we have the index information for the user, for the item, and using the user ID, we take this row and this singular values and this column, and then we can recover this information. So the linear algebra notation wise, to get here's information, we utilize these ones, and actually we can replace these to this one, and it is decomposed into multiplication of the two matrices. It is the dot product of the entity i's latent vectors plus attribute j's latent vectors equals i's jth attribute values. So it sounds complicated. So you just understand that from the SVD, we are able to decompose into, so user-wise, the latent vectors in the item-wise latent vectors. So this is another visualization to get the rating about the specific user I and the J movie, and we can just compute this dot product, and we can get the label, the rating prediction. So once again, the vector UI represents affinity of user U for the each latent vector, and vector J, Vj represents affinity to the movie J. So you may wonder what the latent vectors in means here. So we currently get the left singular vector, right? From the U, and right singular vector from the V. And here, each specific user has the latent vector representation. So here, contents-wise, so here it has n-dimensional latent vectors. So here eigenvalue, in other words, so left singular vectors. The vector itself represents, it shows the latent vectors, and this as the size scales. So the scale information is currently merged into this one, but still the U preserves latent vector for the user, and this one contains the item-wise latent vector. So that is the essence of the matrix vectorization perspective, the recommendation. So so this term is newly used for the recommendation, right? So even though we use SVD, so we currently decompose into just two matrix-wise the multiplication. So this is also called matrix the factorization, because it is decomposed into two matrices. So that's why we say this decomposition as matrix factorization. And it is factorized into from user-wise matrix and movie-wise matrix. So one difference between these two slides, you may wonder why here has the k-dimensional information and this also has k-dimensional information. And we can, due to the space complexity, and at the same time, we just try to utilize the salient information in this decomposition. We take the partial information from here, something like this. Maybe we can utilize something like this. So we ignore this part. So this is called the truncated support SVD, and this dimension is the same as the K. So we got this. Maybe we don't review all the details about the support. I'm sorry, singular vector decomposition, right? SVD means like that, means singular vector decomposition. I'm sorry. And you need to recall what that means if you're not familiar with, and we just utilize their properties, and we get back to we just try to make use of the mathematical properties, and we can recover the predictions. So this is the example. So interesting part is that we try to predict some the missing rating for the specific user. From the input data, we get this matrix factorization and then try to predict these Rij. So with this way, even though we didn't have information for the ith users, the jth movie's rating in this input stage, but at this part, we got the latent vectors and we can predict, we sort of recover, or we try to guess these rating. So that is the key idea about the matrix factorization. It is like encode the original information by getting, like, we just remove irrelevant information and we just leave the important and salient information at this form. And with this information, we try to recover the original input, like data representation, and then we are able to observe some score which is different from the input. So this is the procedure of the predicting the item rating. So in this case, we assume that here vector is this, here is this, to get the rating for the Alice to the Man in Black movie, and we are able to get this one. So this is the predicted rating. So in this case, here k is equal to 3, for example, and this factor 1 and factor 2 and factor 3 could be something like action and comedy and romance. So it is learned from the SVD, and so we are able to see the score and we understand, oh, Alice is a fan of the comedy movie, and so it is the Alice is the preference toward the latent vector is 0.2 and 0.5, 0.3. But the preference is on the comedy compared to the action and romance. But still likes the another genre, but not as much as the comedy genre. And the movie wise, so we understand the movie. So from our vector analysis from the SVD, it has higher value at the first vector because Man in Black is likely to be action. So it is an action movie actually, right? So Alice is not super big fan of the action, so it got the lower score. So this is a semantic understanding. So from the SVD, we get this the factor-wise information. We assume that SVD is able to find the underlying factors, and we guess factor 1 could be the action, and factor 2 could be comedy and romance. Here we have visualization to understand the factor vectors. So we have two latent vectors from matrix factorization. We can understand with the example about the latent vectors. Here we have two different latent vectors. So first one, we have these ranges, and second one we have these ranges. And So when we see we have a higher first latent vector and lower second latent vector, what kind of movie you have? Sister Act, Stepmom, Sound of Music, Runaway Bride. And it is like a drama genre in women based. Some movies are chosen in this place. Robot, this place is a lower latent vector, first latent vector, and second latent vector, higher latent vector, and second, I mean. So in this case, Freddy Got Fingered and Half Baked. This is the famous comedy movies, and so these latent vectors means are able to identify these sort of properties, and at the same time we place the users in this place, and now we see the Alice, the preference of the Alices with respect to the two latent vectors. So she likes it seems like she likes drama and not much for the comedy movie, right? And David is placed in the center, and Carol is placed in here. So with this information, we can recommend the nearby movies to the person.